So angularity is the orientation tolerance that is represented by this symbol. So what it denotes is that a distance between two parallel planes inclined at a specific basic angle in which the surface or axis or center plane of the feature must lie. So it means that it refers that all the points on the specified feature must form an angle with the datum reference. So this is where your datum comes in. So now in this example, you can see that there's an inclined hole drilled through this feature, and hence the angle of this axis of this feature in reference to the datum plane A should be controlled within an angular tolerance of 0.05. So it means that this center axis is controlled within this variation. So you can see that in percentage of tolerance zone we have the 0.05, and that is for your whole diameter of 1, whereas for a whole diameter of 1.01, that is for the maximum condition, then it is the variation is going to be 0.1 and 5, because over and above this 0.1 is where you have applicated here 0.005. So this is how it applies to the different hole, because we have a base dimension here and a maximum material condition here. So applicating those two to here, you get the tolerance zone specification. So this is your orientation tolerancing, controlling the angularity of a surface or axis with reference to your datum plane. So next orientation tolerancing is your perpendicularity, where we maintain the median plane or the surface or axis 90 degrees with respect to a datum plane or axis. So this again, in similar to the angular plane, all the points on the specific feature must be perpendicular with the datum. So we can look at this section. So this is a perpendicular through hole machined through this element. So here the perpendicular tolerance zone is for size is 0.005 with a maximum material condition, and it applies to the datum plane of A. So it means that with this dia of A, so wherein we have a minimum condition of 1 and then a maximum condition of 1.01 for A, because this again we have two variations. Even for this dia we have the maximum material condition for this datum plane. So that's why we have two condition, and then again applicating the tolerance to that. So for one condition, that is with 1.00, and applicating the tolerance of width here for the whole of 0.5, and then in the other case the whole of 0.52. So in those two cases of dia of this datum plane axis and then whole dia, so for that the tolerance is going to vary 0.005. So here it is adding to it, it is 0.05, wherein here it is 0.025. Likewise in here, for this it's going to be 0.15, and here it is going to be 0.035, that is applicated onto this. So this is the tolerance zone that is allowed possible orientation perpendicular to your plane of axis of A. So this is your perpendicularity orientation tolerancing. So next, similarly, we have the parallelism orientation tolerancing, that's represented by two angular lines here. So this refers to the condition of a surface or axis which is equidistant at all points from the datum reference. So again, all the points on this surface are to be parallel to this datum reference within the specified tolerance. So here for this surface should be parallel to this datum reference A with a tolerance zone of 0.01. So if we have a reference plane and here, then the maximum variable tolerance in this is 0.01. So this is a parallel orientation tolerance. So next we have the profile tolerancing. So we have two variants to it: profile of a line, that is 2D, or profile of a surface, that is of 3D. So going back to the overview, so here you can see that for this profile tolerancing, it applies only to the feature surface and not to the feature of size dimension. And for this, we can use a datum reference. So this can be used to control the form also without the datum reference. So based on the requirement, you can specify the reference or not. So let us go back to our slide here. So here this profile of a line is represented by an arcual element. So it means that a uniform two-dimensional zone limited by two parallel zone lines extending along the length of the feature. So whatever length it might be, so that surface, a parallel surface is extruded on the both the sides. So that will define the amount of deviation within which the surface should be lying. So this is the profile of a line variation. So if you see in this feature where we have this curvilinear element wherein this is applied to this surface with this reference. Okay, so then in this 2D plane, drawing a parallel line between these two within which this surface should lie in. So this is your profile tolerancing of a line, wherein for a surface it is represented by closing the representation. So it can be applied because generally this is allowed for a 3D zone. So this is one of the most powerful GD&T symbols because this encompasses almost all the tolerance zone that we have seen earlier, because it also encompasses the profile of the line, the straightness. So all those things are included in this. So if you can see that for this, when we apply this profile of surface, then it is applicated on all the views wherein it's all constrained by this 0.02 dimension. So we are getting a strict profile or the form control of the entire object in its 3D view. So next what we have is the runout tolerancing. So runout tolerance also is a very powerful and also easier way to measure on your end of line. So there are two ways of measuring it. It's either the circular runout, that is on a single axis, or if you consider as a surface, then you can measure the total runout. So it can be applied to the feature surface, also to the feature of size dimension, and it obviously requires the datum reference plane to set the comparison limit. So coming back to our slide here, so this for runout tolerance, this is going to be a symbol, and so this is a composite tolerance. Why composite? Because it controls one or more features of the part. It's an inclusive one, that is by executing a 360-degree rotation about the datum axis. So what it does is, in order to use this tolerance, this element will be rotated along this axis of rotation, and wherein the runout will be measured. That is, you can see in this example here, for this feature, the runout is controlled on this surface. So it means that the maximum variation is 0.01 with reference to the datum features A and B. So for these two datum axes A and B, the feature is rotated upon it, and we have a circular dial gauge that is fixed onto a single point, and the variation of this circular dial gauge along this axis on the rotation 360 rotation should be within a maximum dimension tolerance of 0.01. So this is your circular runout. So this is all is applicated to all the components that have a rotational mechanism where the rotational surface, the 2D feature, to be controlled, because any undulation might result in a failure of the function. So in those cases, this circular runout is a very powerful tool of controlling the runout tolerance. So then we have a total runout. So here we have one more addition to this line of the circular runout. So what it does is, it's again a composite tolerance wherein the entire surface elements are mapped within that runout zone. So if we apply it to this full zone, so it means that you are running this dial gauge onto the surface along this entire length of the feature. So this entire zone at all the points should lie within this 0.01 dimension tolerance. So this is your runout tolerancing. So next we look into the modifiers that we can apply to the tolerance zones. So first is your regardless of feature size. So what it means is, this is going to be the default condition for all geometric tolerances by rule 2. So this GD&T rule that we'll look into in the next slides, but typically this is the basic tolerancing. It means that if you do not mention any modifier, any symbol to it, then by default it means that the feature is controlled regardless of the feature size. So it simply means that whenever there is this reference, that is, there is no symbol that is referred to here, then the size, this tolerance is going to be controlled irrespective of the feature size. So it means that this tolerance zone is strictly pertaining to this only tolerance axis. So the actual size is going to vary from 1 to 1.01, and on this the tolerance zone is strictly applied. So simply saying, this is what we have seen in the earlier examples of your form tolerancing, because you do not have the datum references, so it is strictly applied to the size of the dimension without any independent control. So next what we have is the one more thing is that this regardless of feature size is eliminate any additional bonus tolerance that we get when we refer to a datum axis. So this is a very tight method of controlling the datum features. So it is always used for runout, concentricity and symmetry based controls, and also in case of external or internal features, that is a hole or a circular the external a fillet kind of thing, then it is used to control the wall thickness variation with this modifier. That is, you are strictly restricting the maximum boundary that it can exceed. So this is your regardless of feature size. So next what we have is a powerful tool, that is the maximum material condition, that is represented by the symbol M. So here this is a feature of size that contains the maximum amount of material everywhere within the stated limits of size. So it means that the tolerance is at the extreme. So tolerance is applied to the extreme. So in that condition, it would result in a very little material is removed, so that maximum material is retained within the feature. Suppose if the MMC is applied to the internal feature, then it's going to be the smallest allowable size that is removed out of it. In an external feature, it's going to be the largest allowable size. So this maximum material condition, there are restrictions to use it. These are applied to features that are incorporated to the axis or the median plane. So it cannot be applied to a flatness, roundness, cylindricity, profile of a plane, profile of a surface or runout. So this maximum material condition is applied only to those features that incorporate an axis or a median plane. So let's look into this example. So here we have a datum reference of A here with this that is controlling this external feature a maximum of 2.01, and here this surface is of 1 to 1.01, and quotient tolerance is controlled using a maximum material condition and with reference to the surface A. So it means that with the actual size of 1 to 1.01, the maximum variations that it can go is this. So for this the maximum is 0.01, whereas for this it can extend until 0.15. So this is the maximum condition that we get. So please refer to your the previous slides where we had looked into the flatness conditions, where the maximum material condition was covered. So this is how you allow the maximum material that is to be retained within your material. So this is applied to your straightness, not to flatness, but this to the straightness. So next, the opposite condition for MMC, we have the least material condition. So this is a feature of size that's going to contain the least amount of material everywhere. So it means that the tolerance will be at the minimum most extreme, that would result in a condition with only a large amount of material that's going to be removed from the base feature, so that minimum material is going to get retained. So this LMC will ensure that all the components are prevented being assembled. So it means that much material is cut off, then it prevents the component from assembled. So this LMC symbol condition is always used to assure a minimum amount of machining stock that has to be retained so that it can be comfortably assembled, because beyond this the function of the components does not get satisfied. So this gives the minimum most condition so that the feature can be measured and can be used for the assembly of the components. So this again with this example in this zone, when applying to the least material condition, so it means that this is getting alternate. So only with the maximum condition is here 1.01, that is where the max tolerance zone is applied, whereas the maximum material condition for a tolerance of 1.01, the tolerance zone is going to be 0.5. So thereby we are controlling the maximum material Whereas here, even with the minimum meeting envelope of this, and with this tolerance, we are assuring the minimum material that is available for the components to get assembled. So this is your least material condition. So next in modifiers, we'll see the additional 3 modifiers that can be used at our disposal. So first thing is the projected tolerance zone that is represented by the symbol P. So what this does is, so far whatever we have seen applies only to that feature, that is all the modifiers and the symbols apply only to that feature surface. Whereas using this projected tolerance zone, in case of mating components, this tolerance zone can be projected onto the other features mating part, creating a virtual zone of tolerance. So this is highly useful for mating features, that is two interacting components. So this is your projected tolerance. So for example, this can be applied to a bolt and a hole or a shaft. So those kind of features, to align those tolerance zones, you can do. So this is useful for stack up analysis of your assembly. So next is the unequal tolerance zone represented by U. So all the tolerance that we specify to the form are equally distributed about the true profile, whereas sometimes in some areas where in one end of the profile we need to have a unequal zone, then you can override that control using this modifier. That is, on one end you control on the higher side, on the other end on the lower side within the tolerance zone boundary. That is, you are disposing the tolerance zone unequally. This is done by the command of U. So next what we have is the tangent plane modifier represented by T. So this is an easier way to control the surface, because so normally in any tolerance, so suppose if you consider the flatness or parallelism, then what you are doing is each and every point on that surface have to align to the parallelism tolerance. Whereas if we apply the tangent plane modifier to this, it means that you position a tangential plane to the high points of the surface, so that instead of considering each and every point, the high points of the surface, if that is tangential to the surface, comes within the tolerance zone of parallelism, then you are satisfying it. So this also removes the bonus tolerance that we had seen earlier in the MMC condition, that is with maximum material condition. We have an additional tolerance that can be removed because we are specifying the high point from this surface. So this is the tangent plane modifier. So based on specific manufacturing technique requirements and inspection techniques, you can opt between these modifiers to control the form or profile of your feature. So moving forward now to the rules of GD&T. So this is basically whatever we covered in the earlier slides. So going by one, the first rule is that the individual feature of size or the perfect form at the MMC or the envelope rule condition. So typically what it means that when only a tolerance of size is specified, that is only the maximum tolerance, that is the size of tolerance is specified. Suppose example dia 50 with a variation of plus or minus 0.001 mm. So it means that only size tolerance has been specified. Then the limits of size of that individual feature prescribe the extent to which the variation in geometric form as well as the sizes are allowed. So simply means to say that suppose if we operate on the maximum material condition with this only size tolerance, that is of 50 mm dia with a maximum tolerance of 0.001. In that case, it means that at 50.001 condition, that is in your maximum material condition, no more tolerances allowed. That is, we don't have any other modifier in that case. So in that case, for an MMC, it means the external surface is of perfect form without any undulation or without any errors. So this is the rule number 1 of your GD&T. So next rule is that regardless of feature size that we had seen earlier. So it means that unless specified any specific modifier, all the default modifiers are considered to be regardless of feature size. So it means that with respect to the individual tolerance, the datum reference or both of it, where there is no modifying symbol specified. So therefore, we always need to have the MMC or LMC are sufficient modifiers to be included in the drawing. So these rules like hard and fast override the GD&T tolerance zone we are providing. So it means to say that unless we override this using modifiers, whatever feature of size that we are machining will pertain to the perfect form size without any undulation if it's going to be in the maximum material condition or in the regardless of feature size condition. So always we need to consider the manufacturing processes that we have in hand and use these modifiers diligently to ensure that the form, fit and function of the feature gets satisfied. So finally, putting all these whatever we've seen together in the GD&T encoded drawing is your feature control frame, wherein it has different compartments. So the first compartment is the geometric characteristics symbol that we have, either a form tolerancing or a orientation tolerancing or a profile tolerancing. So that symbol is drawn first, followed which the tolerance zone descriptor, so that is where does it applies to. So for example, this tolerance, the true position tolerance applies to the diameter of the feature, and followed which what is the tolerance of that location. So here that tolerance is specified, the tolerance zone is specified, followed which the modifier is added. So here we have given the material condition. So it is the maximum material condition or the minimum material condition or the tangent in plane or the unequal tolerance zone. So all those modifier symbols are then placed in this compartment. So next we have compartment based on the requirement. Those are all filled with the primary, secondary and tertiary data planes. So if we have only the primary datum reference, then we can restrict with this compartment itself, or if we go on for other compartment references, then you can add into it. So this is what consolidates all the GD&T symbols, modifiers and applications that will control the overall tolerance of the feature. Finally, what we've seen is we can insert this GD&T tolerance using this feature frame reference. So what we can do in the AutoCAD environment is that we can call upon using the tolerance command. So before that, for ease of understanding, let us just construct a rectangular element. So consider this to be the cross section of a circular shaft. So in that manner, so let us apply a tolerance to this surface. So towards this, we can invoke this by using the tolerance command TOL, followed with we get this dialog box for the geometric tolerance. So here you can see the various compartments that are available to it. The first is the symbol, this GD&T symbol. If you click on this bottom, then you can get all the form, location, runout and the profile tolerances along with the orientation. So we have all the symbols listed here. Based on requirement, on clicking it, it will get inserted. Next is the tolerance zone specification. So here we have a prefix as well as a suffix. So this text box calls in for the numerical value of the tolerance considering 0.001, and in prefix we can add whether the dimension control symbol is applied to this or not. So clicking on this will enable the diameter control. So as is the position tolerance, then you can use it here, or if it's not required for in other tolerance cases, then you can remove this. So we'll keep this one here. So but right now we are just looking to the flatness, so we are not looking for the position here. So for this tolerance of straightness with 0.001, and then this applies to the which material condition. So consider this to be the maximum material condition. So AutoCAD also refers to the regardless of feature size as material S, but by definition and by latest updates we do not require to have any symbolic representation for that. So hence you can just go with either the maximum or least, or leave it as it is for regardless of feature size. So assuming let's go for the maximum material condition, then also we have one more tolerance that we can take it for the unequal tolerance zone conditions, but currently let us not go with it. And next we have the datum reference features plane that can be called upon. So here you can type in the datum reference planes. So suppose we have the datum reference plane A, and additionally the modifiers can be applied to this specific datum. So we have applied this maximum material condition to this datum. So apart from that, we also have this projected tolerance zone available. So this projected tolerance zone contains the symbol of that along with the height and datum identifier. So this height creates a projected tolerance zone value in the feature control frame, and it controls the variation in height of the extended portion of a fixed perpendicular part, and thereby refining the tolerance that is specified to the position tolerance. So this is what is controlled by the height for this projected tolerance. Next, for this projected tolerance, what is going to be the datum identifying symbol? So this is the projected tolerance range, wherein this is your normal feature reference. So just for clarity, we'll just put out a value here to see how it acts upon. So now the next requirement is to position where the tolerance location needs to be held. So here you can see that the feature control frame is neatly positioned with the GD&T symbol, the tolerance zone, the material condition, and the reference zone, as well as here we also have a projected tolerance zone condition with its reference plane. So this is the representation of the tolerance zone, feature frame referencing in here. Feature control. So one more thing is that you can individually apply the leader to this dimension annotation text of tolerance. Alternatively, we can also do the same by using the leader command, invoking the leader. So suppose let's say specifying this point and for this angle, and now we can select the annotation, and in type of the annotation, when clicking on enter, we'll go for the options, and here we can select the tolerance option. So now this again calls for the geometric tolerance input box, wherein you can specify this your conditions, so that will get applied onto here with the leader. So this is how the tolerance feature control frame with leader and such is applicated onto your AutoCAD drawing.